session with a talk by Alex Liu, who is working at MIT, and who will present his talk towards denotational semantics of AD in higher order recursive and probabilistic languages. Thank you, Alex.
Great. Thank you, Christine, and thank you to the organizers. My name is Alex Lev, and I'll be talking about some work done jointly with Mathieu and my advisor, Vikash Mansinghka, about the denotational semantics of automatic differentiation. So probabilistic programming languages use AD a lot, for example, to compute derivatives of probability density functions, or estimate gradients of expectations for variational inference, or compute change of variable corrections in reversible jump MCMC, like Frost showed in the last session. And if we want to reason about the correctness of these algorithms, we need a couple of things from a semantic framework. First, we need our semantics to handle AD and probability jointly. For example, let's say we want to verify a two-stage program transformation for computing the gradient of a probabilistic program's density function. The first stage translates a probabilistic program into a deterministic density function, and then the second applies AD. We need a single framework that can interpret the original program as a probability measure, interpret the transformed program as a differentiable function and verify that it is a density of the first program, and of course interpret the result of AD and verify that it is a derivative of the density that we computed. A second goal for our semantics is to cover a Turing-complete programming language. Probabilistic programming, almost from its inception, has recognized the power of higher order and recursive functions as modeling tools, for example, to implement stochastic processes or adaptive grammars in natural language processing. And in many modern probabilistic programming systems, higher order recursive functions like map signal conditional independent structure that can be exploited for faster inference. This is also similar to the point that Roy made in his talk earlier about higher order primitives. They're really useful, and our semantics shouldn't require that we give them up. So in this talk, I'm going to present some ongoing work that aims to meet these goals. Our starting point is a paper by Li et al. About the correctness of AD in the presence of if statements and piecewise functions, which I'll spend a few minutes reviewing. We're then going to extend their work to cover an expressive language with higher order functions and recursion using ideas from several recent papers. At the end of the talk, I'll briefly discuss applications of our semantics to the probabilistic programming areas that we talked about earlier, drawing on examples of algorithms and theoretical results from the literature that our semantics may shed new light on. Okay, so let's get started. The key picture to keep in mind when we're talking about denotational semantics of AD, which I'm adapting here from Huot et al. 2020, is a square that looks like this. We have the user's program on the top left. We can apply AD to the program and get another program on the top right. The semantics allows us to interpret each program as defining a mathematical function and verify that the second function is the derivative of the first. If our language is sufficiently simple, this picture holds up without any further modification. For example, here's a very simple language for differentiable programming. Programs in this language can be interpreted as functions of an input vector x. So a constant c denotes the constant function. The subscript x sub I denotes the ith element of the input vector. And a program that calls f denotes the function that, given a vector x, first computes the arguments to f, and then runs f to obtain a final result. Now, every program in this language denotes a differentiable function, which we can differentiate using a pretty simple AD macro that just applies the chain rule. Things get trickier when we add if statements, which can introduce discontinuities. This is the language that Li et al. Considered in their 2020 NeurIPS paper. So our semantics interprets this language's programs as functions like before, but not necessarily differentiable ones because of the hard comparisons like greater than. So even though we could define some behavior for what AD should do when it encounters an if statement, it's no longer clear what the correctness criterion is. What should AD compute when the derivative doesn't exist? So to resolve this difficulty, Li et al. Introduced a notion of a PAP function, which stands for piecewise-analytic under analytic partition. Let's break down what that means and why it helps us address this semantic issue. For a function f to be PAP, it just means that you can write f piecewise, with countably many pieces, where the pieces are nicely shaped and the functions are well-behaved. So the specific notions of well-behaved and nicely shaped here are analytic functions, which is a slightly stronger condition than smooth, and analytic sets, which are sets carved out by finitely many inequalities of the form g of x is less than or equal to 0, where g is an analytic function. So if you picture a PAP function, it looks something like this. We carve up the domain with these pink lines showing the zero sets of these analytic functions that are in the inequalities. And then within region I, f's behavior is determined by some analytic function fi. Now, Li et al. Showed that in their language with if statements, if all the primitive functions are PAP, then so is any program. Which is nice, but since PAP functions are not necessarily differentiable, it may not be clear how this resolves the original semantic issue we faced. What does it mean for AD to be correct on these piecewise functions? Li et al. Also introduced the idea of an intensional derivative of a PAP function. If f is a PAP function, and if there exists some piecewise representation of f for which g is its piece-by-piece derivative, we call g an intensional derivative of f. You say an intensional derivative because intensional derivatives are not unique. There are many ways of writing f down as a piecewise function, each of which might lead to a different intensional derivative. But any two intensional derivatives are going to agree up to a measure zero set of inputs. And using this definition, Li et al. Were able to show that AD always computes some intensional derivative of the user's original program, even though which intensional derivative it computes might depend on the source program's implementation details. This framework gives us a way of reasoning about AD's behavior in the presence of conditional branching and piecewise functions, and is a good starting point for adding higher order functions in general recursion. The challenge here is that if you look at Li et al.'s language, every term denotes a function from this vector x into the reals. So they can say a term denotes a PAP function whenever its subterms denote PAP functions, and that's the basis of an inductive proof that all functions are PAP. In our language, not every term is going to denote a function between Euclidean spaces. We're going to have higher order functions and some partial functions. And in order to carry out a similar inductive proof, we need to generalize the notion of PAP so that it can be applied to terms of different types. In order to do that, we're going to use the same tools that were recently used by quasi-Borel spaces to generalize measurability beyond measurable spaces, and diffeological spaces to generalize smoothness beyond manifolds. Our PAP spaces are going to generalize this notion of PAP beyond Euclidean spaces to other spaces x and y. So we're going to try to answer what is a PAP function between two other spaces. As a first step toward defining this idea of a PAP space, let's define a C-analytic subset of Rn to be a countable union of analytic sets. Now, say you have some arbitrary space x that you want to think about PAP functions into and out of. The first thing you have to do is tell me for each C-analytic set U, which functions from U into X should we count as PAP? And these functions are going to be called plots in X, and it's a choice that's up to us how to choose them. So for example, consider X to be the Booleans. Which functions from U into X should we consider PAP? One intuitive answer is we should be able to write the function piecewise, carving up the domain into these analytic sets A1, A2, A3, etc., where on each piece we're either true or false. Another way of saying that is that the preimage of true and the preimage of false should both be C-analytic subsets of U. So this is one example of a choice of plots in a type like bool. When we choose our set of plots, they have to satisfy certain closure properties that I'm not going to go into a lot of detail on right now. But if you satisfy them, we say that you've defined a PAP space, an underlying set, together with a choice of which functions into that set from Euclidean space we think of as PAP. Now, the key payoff for all the work we did to define a PAP space is that if we have two PAP spaces, x and y, we can say what it means to be a PAP function between x and y. So in particular, if I have a function f from x to y, the rule is that in order to be PAP, if I take any plot in x, and then I compose it with my function f, I need to get that the resulting composition is a plot in y. We can use these PAP spaces to interpret the types in our language, for example, to handle higher order functions. So in particular, we can think about when a higher order function is PAP by defining a PAP space of x to y functions. Our underlying set is just going to be all the PAP functions from x to y. And then we'll have to choose our plots. Which higher order functions from this Euclidean space into this function space do we want to consider as plots? Well, if we have one of these functions phi from u to x to y, we can look at its uncurried version, which is just a first order function from u cross x into y. And if we define what product spaces mean in PAP land, we're then just able to ask, is this higher order function, does it correspond to a PAP function from the product space x cross y or u cross x into the PAP space y? So this gives us a way to interpret higher order. We can carry out a similar exercise to support partial functions. A partial function is just a function into this space x bottom, which has all the elements of x plus a newly adjoined bottom element. And a plot in x bottom is just a piecewise function where on each analytic set in the domain of the function, you're defined by some f that's actually already chosen to be a plot in x. But these analytic sets don't have to cover the full space of U. There's this extra otherwise clause that sends anything that you didn't cover to bottom. This otherwise clause is really important because it can apply to a collection of inputs that couldn't otherwise have been divided up into analytic sets. We made this choice because in a Turing-complete language, it's possible to write recursive functions that fail to halt on very weird sets, like this one, which loops forever when the input is a member of the Cantor set. The Cantor set is itself not C-analytic, which means there's no way of writing a piecewise function where bottom cover is neatly divided up into some of the pieces here. Handling recursion in general requires another extension beyond just handling partiality that I'm not going to go into, except to say that we can define an omega-PAP category very similar to omega-diff and omega-quasi-Borel constructions, which were used to add recursion in those settings. And that gives us the structure we need in order to give a semantics to our full language, interpreting every program as some omega-PAP morphism. We can also prove AD correct for a slightly generalized notion of intensional derivative. And I'll post these slides on the LAFI website if you want more details. But for now, I just want to summarize the key conclusions here, which is that first, even when you use higher order and recursive functions in your program, if at the end of the day, you wind up with a total function between Euclidean spaces, then it's PAP in the same sense as in the original Li et al. Paper. Second, even in languages with recursion and higher order functions, AD computes correct intensional derivatives, which agree almost everywhere with actual derivatives. Third, when you have a partial function between Euclidean spaces, these results all still hold if you look at just the domain where that partial function is defined. So how do we use all this to make interesting conclusions about probabilistic programming? So following the work on omega-quasi-Borel spaces, we define a monad M of measures and add probabilistic programming constructs to our language. This is pretty involved. I'm not going to get into it, except to say we can sort of interpret sample and score and the monadic glue needed to construct probabilistic programs. What I really want to do in this section is look at some examples of what happens when we try to combine AD and PPLs. The first one is the one I find most interesting. It's inspired by Rodel and Alexiev's AI stats paper last year. The idea is that in many probabilistic programming languages, primitive distributions come equipped with a density function and a sampler. So here's a program that samples points in the unit circle uniformly at random, and a corresponding density function which returns 1 over 2 pi at any point on the circle, 0 elsewhere. Now let's say that the user has written an invertible deterministic function f. In this case, f just is performing a linear transformation to stretch this thing, but it could be more complicated. Some probabilistic programming languages will automate the construction of a new sampler and density representing the push forward of the original distribution by f. Now the sampler is really easy because you just run the old sampler and then run f on each sample to get a sample from the new distribution. But the density is more interesting. Some parts of this distribution have been stretched thin, others compressed, and that's captured by a change of variables formula, which tells us exactly how to compute the new density based on the old density and the Jacobian of f, which is used to compute this V prime matrix in the denominator here. Now, if we look at f's definition, we can easily compute the Jacobian, but what if it was implemented slightly differently by the user? So this code implements the exact same linear transformation as this code, except when you're on the unit circle, if x squared plus y squared equals 1, and x is greater than 0, so if you're in the right half of the unit circle, it uses square root of 1 minus y squared instead of x. And that's going to cause AD to compute the wrong Jacobian. So I'm showing here what AD would compute at the point 1 over root 2, 1 over root 2, but actually AD computes the wrong Jacobian at every point on the unit circle. Okay? What's weird is that remarkably, when you use the wrong Jacobian to do the calculation, you wind up with the same answer as when you use the right Jacobian. So is this just a lucky coincidence? It turns out that the answer is no. We proved that when using this change of variables formula, any intensional Jacobian, so any Jacobian full of intensional derivatives, will give the same answer. In some sense, even though AD is wrong, our semantics shows that AD is wrong in the right way. Next up, let's look at differentiating densities. Here's the image from the intro slide. We have a probabilistic program, a transformation that creates a density function, and another transformation that takes its gradient. Our semantics can interpret this probabilistic program as a probability kernel, validate that the density that we compute really is a density with respect to the base measure of interest, and our correctness proof for AD handles this part of the diagram. If you might be familiar with Mak et al.'s result from last year that almost surely terminating probabilistic programs have almost everywhere differentiable densities. And if so, you might wonder where this almost sure termination comes in our picture. because we have here that the deterministic density function from any probabilistic program is going to be an omega-PAP morphism. And from Lee et al.'s original work on PAP, we know that PAP functions are almost everywhere differentiable. So what gives? Not all probabilistic programs have almost everywhere differentiable densities. What happened to this almost short termination requirement? Well, the trick here is that this trace density that we compute is actually a partial function. On some traces, on some lists of real numbers, it outputs bottom, or it loops forever. And when we're verifying that it's a valid density, we interpret non-termination as 0, as a density of 0. These partial PAP maps are only guaranteed to be almost everywhere differentiable on their domains of definition. So if we really want the density to be almost everywhere differentiable in general, we need to also show that this omega-PAP morphism is a partial function defined almost everywhere. And almost short termination ensures that it is almost everywhere defined. So that's where the almost short termination comes in. And we get a kind of denotational view of this result that was proved more operationally in the Mack et al. Paper. I want to just end by talking about one last thing that we haven't really figured out how to explain using our semantics or any semantics, which is stochastic optimization. And the big question here that we really haven't addressed is how should AD behave when applied to a probabilistic program? Not a density function derived from a probabilistic program, but the probabilistic program itself. And one somewhat appealing answer might look like the image on the right here. We have a probabilistic program, we do AD, we get a new probabilistic program whose expectation is the gradient of the expectation of the original program. This would give us a way to use stochastic gradient descent to optimize expectations of programs. Each run of this probabilistic program on the right gives an unbiased estimate of the gradient of the expectation, which can be used in stochastic gradient descent. Now we have a monad of measures, so we can interpret probabilistic programs as kernels. There is a morphism implementing the expectation operator, but it's into this weird space called W instead of the reals. And W has a different set of PAP plots that makes it less useful in this case, but was necessary, we thought was necessary in order to make everything go through. This is not just a weird semantic issue. We actually don't know of any AD algorithm that unbiasedly estimates gradients of expectations under arbitrary probabilistic programs, but there are papers that do it for simpler languages than our language, that don't have recursion, don't have higher order functions, and have simpler primitives. And we're looking at these right now to see whether our semantics can explain why they work and perhaps help to generalize them. So I think I'm out of time, but I'll leave this slide up, and if there's time for questions, I'm happy to answer one. Thank you.
Okay, thank you very much, Alex, for this great talk. We have 1 minute perhaps for Huot's question. Huot, do you want to ask it?
Oh, yes, just very quickly, have you looked at recursive types?
Yeah, so I mean, we're following pretty closely the same development as in the omega-diff and omega-PAP. So I think that we have, we're doing the axiomatic domain theory thing that was in your paper and Matthias's paper. So yes, I think we can handle recursive types.
Yeah, it's not to check, but it's kind of cool that it just checks out.
Yeah, exactly. So I've been going through all the axioms.
Okay, thank you very much, Alex. I think we have to move to the next talk.